Hi, I'm Harshit, and this is a presentation on work SMORE, score models for offline goal condition reinforcement learning. GCRL methods can roughly be divided into four approaches. These include RL with sparse rewards, iterated behavior cloning, contrastive RL, and occupancy matching. Goal condition RL with 0-1 rewards implies learning a Q function that predicts the probability of reaching a particular goal from a particular state and action, making it a density model. Modeling density is a hard problem and has prompted exploration into other ways that make optimization easier. The second class of approaches for GCRL frame RL as a iterative supervised learning problem, where the goal-reaching policy is deployed and trajectories are relabeled with actually achieved goal. The process is repeated until convergence. Iterated behavior cloning methods are provably suboptimal in the online setting. In this work, we deal with the offline setting where the iterations are not even allowed, as we do not have access to the environment. A recently developed line of methods, contrastive RL, have achieved success in solving high-dimensional GCRL problems. They avoid the problem of density estimation in sparse GCRL by instead learning a density ratio using classification, as classification is an easier problem than density estimation. But in the offline setting, it has already been shown that contrastive RL methods do only one step of policy improvement and does not give the optimal policy. The fourth line of work frames GCRL as an occupancy matching problem between the visitation distribution of the current policy and a distribution centered around goals. The method works by first learning a discriminator between the goal distribution and the offline data distribution and using that as a pseudo reward in the subsequent RL step. Unfortunately, using discriminator as a reward function can lead to compounding errors for RL step and lead to performance degradation. The key question that we ask in our work is, how can we derive a performant GCRL method that learns near optimal policies from dataset of suboptimal quality? We use dπg to denote the discounted probability of reaching a particular state action under a policy πg. Rho is the state action goal visitation from which our offline dataset is sampled. The transition operator on the score function S computes the expectation of function computed on next states and next policy actions. F divergence represents a measure of distance between two distributions where F is a convex function. The convex conjugate of F can be obtained using the convex conjugate definition shown below. We define training and testing set of goal distributions denoted by qtrain and qtest respectively. Usually, a wider training distribution of goals is used to make learning more efficient. We define a goal transition distribution denoted by Q that has probability mass on transitions leading to goal with probability proportional to the transition probability. Our proposed method leverages the insight that matching policy visitation to goal transition distribution probably solves the max entropy GCRL problem. Two questions remain. First, how do we compute dπg, as it requires deploying the current policy in the environment, but we do not have access to the environment in the offline setting. Second, how do we leverage suboptimal offline data rho? We propose matching mixture distribution of policy and offline data visitation to mixture distribution of goal transition and offline visitation. The key benefits of this algebraic manipulation are that now we can leverage offline data to solve GCRL as well as compute a dual problem that is completely off policy. The dual problem to the mixture distribution matching problem results in an optimization objective for our method SMORE. SMORE is a min-max optimization between a score function S and a policy pi. The intuition becomes more clear when we substitute F with a divergence. In this slide, we use the chi-square divergence. SMORE's objective decreases score under the current policy πg and increases score at the proposed goal transition distribution while enforcing a L2 smoothness under dynamics. The score function learns unnormalized values that represent the utility of taking a particular action learned via contrastive procedure. Our experiments on a wide variety of domains show that SMORE results in improved performance on the offline GCRL benchmark, often outperforming by a wide margin. Discriminator-based baseline to GCRL suffers from when the offline data set has a few goal-reaching trajectories as a result of compounding errors from the learned discriminator. SMORE is one of the first approaches alongside contrastive RL that scales to image-based GCRL, but in contrast to contrastive RL, optimizes for a near-optimal policy. Thank you for listening to the talk. Please visit the website for more details.